Thank you very much, Georg, for this really impressive talk. So please take a seat for our panel discussion. I'd like to ask Yulia if she's still around, either behind the stage or in the public. I hear her coming. So we can start some common discussion. Please decide which one, maybe. Okay, so I should go to the center. And there's another microphone here. Actually, it would be more practical if you stay in the center so you can maybe exchange that microphone. Yeah. Okay, so there have been quite some questions. I'll try to ask them by grouping them in such a way that they can be somehow applicable to both of you. Although there's still some time for the audience to ask questions to Georg, who was the second one speaking. So please don't forget to type in your questions in Huva, in the app. Okay, so I would like to start with a general question that has been mentioned already in the first discussion, the source of the data. And this has been called the elephant in the room, the problem of data scarcity. To what extent does this issue affect your approaches, and where do you get your data from? You already mentioned some, but...
Yeah, I guess I can start. So for simulations, of course, we need the data from traditional physical simulators to train our neural network models. But the hope is that, or not even the hope, we have shown in the previous papers that you can train the network on the small simulations and then use the network to generalize to bigger simulations. So then the advantage of using the neural nets is really the speed. But yeah, originally you actually need the physical simulators to get the data. And if you're curious, so the data sets that we use, so BoxBath is a standard data set for the physical simulations, and then for the 3 other environments we used MuJoCo physical simulator. And yeah, we use only like positions and velocities at each time step for each of the objects, so that's our data.
Yeah, so for us, it's also so that in simulations we can relatively easily collect data, but then whether this will really work for the real system is a big problem. So that's why we are looking mostly now into like transferring the models, so training the models, pre-training the models on the simulation where it's relatively easy to collect data, but then being able to fine-tune them on the real robots. And something that we have also been doing now is to develop a set of robot platforms which are identical for this manipulation tasks, and actually in a way that people from outside can actually log in and run their code a little bit like a cluster. It's called Real Robot Challenge. If you want, we want to launch this again this year. So if you're interested.
Okay, thank you very much. Now, connected to that is another question on how the performance of the approaches scales if you start having, for instance, in your case, a lot of different constraints. And I guess in your case, if you start having a simulation of real robots as maybe the starting point. So can you comment on that? Also, in your case, you had constraints as well based on the adherence of the planner to the policy. If you start having many of these constraints, how does the performance change or scale?
It's interesting that we are getting really the same questions for like physical simulations and RL. I'm actually impressed by this. Yeah, so scaling for the physical simulations, the biggest environment that we've shown was 1,024 nodes, but actually GraphNets can scale really well to like thousands of nodes, and that's our previous work from the group and DeepMind. So we didn't really see much issues with scaling in terms of running the graph network. There is a little bit of an issue with the fact that we run several iterations with gradient descent, and then we need to backprop through it. So there since it's an iterative model, we run into issues with like vanishing gradients, and similar to what you would see in recurrent neural nets. So we are working on fixing that. Yeah, but overall, it's the GraphNet scale really well to many nodes and many particles.
Yeah, so maybe because I was talking about a few different things. So the first thing maybe about the scaling of this black box optimization method or this planning method, it was for me very astonishing to see that this works on this problems with like 25 degrees of freedom and like 30 time steps. So it's hundreds of dimensions that you're optimizing over, and still you're getting a decent result. That was really sort of mind blowing to me. But I don't know how far you can take that. But when it comes to this model learning part, it's really a problem that if you want more and more complicated models, that they won't run at real time when you run the planning. So at the moment we have a GPU implementation of those, and we can run them at about 30 Hertz with the entire planning cycle in, but they are not terribly complicated models yet. And so with the safety constraints, yeah, at the moment these are manually iterated over, so the more constraints we will put in, the slower the system will be. So at the moment we have only a few of them. And that's a big challenge, yeah. And the question is, where should they actually come from, right? So.
Okay, so you just mentioned optimization. That is another keyword that there are a few questions about. So you've been showing mostly gradient-based optimization. You've rather shown sampling-based optimization. So one question is, why did you decide on one versus the other? And did you ever encounter issues regarding the non-convexity or the non-convex nature of this optimization? So did you ever have the experience of being trapped in a local minimum and not being able to hit a better minimum? How did you cope with these issues with non-uniqueness, let's say, of the minimization? Ladies first.
Yeah, so with the gradient descent, we chose it because we wanted to define this constraint function as a minimization, and it is also a differentiable procedure, so then we can backprop through all the iterations of gradient descent. And sorry, what was the second question besides?
The non-convexity, so the
right, non-convexity. Yeah, so we didn't have any issues with that and didn't enforce the convexity in any way, even though the constraint might seem convex, just through the training of this function through gradient descent. It happens to have this funnel-like shape that is easy to optimize with gradient descent. But of course, if we wanted to, we could enforce convexity.
And Yulia, since you have the mic in your hand, there is a specific question regarding this, regarding the plot you showed for the pendulum, where the error apparently started to increase again after a large number of steps. Right. Can you comment on the reason for that? Was that an issue?
Yeah, so there we looked at the actual plots of the constraints, and it seems that after so I've showed that the accuracy decreases from like iteration 1 to 9 and then goes up after iteration 9. So we think that the gradient descent just overshoots kind of the minimum of the constraint because we use the constant
step size.
Yeah, constant step size. And I think there was a question about the step size as well. So
yes.
Yeah, so we use just a constant step size because we tried adaptive step sizes to to make a faster convergence to the minimum, and from our experience it didn't work too well. But you know, as always with deep learning, you can try a little bit harder and make it work. But yeah, we chose constant step size mostly for the sake of simplicity.
I guess, I mean, you have the luxury to optimize your optimization landscape, right, yourself. So you can actually create the landscape, and it will then be more or less optimizable with gradient descent. On our case, when we do this path planning, this is a highly non-convex problem. If you go left or right around that object, I mean, if you have this cartoon picture in mind, then gradient descent will clearly go in one of the two and wouldn't find the shorter one. And these problems in contact-rich simulations or contact-rich situations is really abundant, and gradient-based methods really have very, very hard time to work there at all. So these sampling-based methods seem to really be a way to go. And so, yeah.
Okay, so I have a curiosity from myself, waiting for possible more questions, is in both of your cases, did you try or are you planning to extend the approach to deformable context? So like in your case, the constraint was basically contact to a rigid obstacle. Did you try already contact between two deformable objects? And did you try to use this for continuous bodies, or are you planning to use this for continuous bodies rather than particle-based, let's say, systems? And in your case, are you going to stick to, let's say, rigid robots, or is there a plan to extend the work to soft robots?
Yeah, so in our case, I think the fluid was kind of the closest to the soft constraints that you're describing. And also in our previous work from the group, we tried the graph networks on the cloth simulation, so that is also soft constraints. But yeah, for now, we tried the constraint-based model only for fluids. So it's possible to use it for soft constraints, but yeah, besides the fluids, we haven't tried any other types. And sorry, what was the second question?
Okay, I mean, you partially already replied, because when mentioning the cloth simulation, that is a continuous body rather than a
Continuous
particle
body.
type.
Yeah, so it's a little bit hard to use it for continuous bodies because we need a graph, so we rely that there is a discrete set of particles that models this space. So for now, it's unclear how to use it for continuous bodies.
But you could have a discretized continuous body, no, in principle.
Yeah, that is actually, that's a good thought. So yeah, maybe we can chat about that a little bit more.
Okay, and then.
Yeah, so I think the beauty of our work is in principle that it doesn't rely on the fact that we have a rigid body dynamics. I mean, if I learn a model, then I can learn the model for anything. And so, yeah, we really would love some applications to some soft robots and so on. We don't use them mostly for convenience reasons because we have this classical robots in the lab. But it would really be cool to see some applications. So if you guys have some and want to try it, please come and contact me and we do something.
So I think you had especially the keyword real time, right? So that is really what you're aiming for. And probably in your case, it's not real time for the sake of controlling a machine or a robot, but just to achieve really quick simulations. How do you see the current state of the art, including of your work, in the compromise between accuracy and real time, or let's say high speed? Do you think do you still see a lot of room for improvement, for instance, in your own approach in speeding it up further, or you're pretty much hitting the limits of what can be done?
In terms of time?
Yes, in terms of, of time, but also of compromise between accuracy and time.
Yeah, I think for us, we would want to have faster models or more complex models that still run in real time. So we have already parallelized the ensembles on the GPU, and all the optimization, everything runs directly on GPU, never leaves the GPU, that we get anywhere close to the real-time constraints. And yeah, we are suffering from the fact that the models can't be more complicated than we would like them to be. So we are looking for better models and faster GPUs.
Better models meaning faster models, so not more accurate.
I mean, the ones which are running fast. I mean, in particular for this rigid body simulation, and we are also looking soon into the graph nets, because we think that they might be very useful for this simulation of the robotic systems, because normal MLPs are just not really great, honestly.
And regarding accuracy, are you, let's say, satisfied with the accuracy, or?
Yeah, I mean, for us, it's more important that these uncertainties, and both is kind of important, that we get some decent predictions, but we also know when we are wrong. And so these both are somehow important, but we haven't really figured out then, or like scanned the entire landscape of what's possible there. So I can't really give a good qualified answer yet.
Yeah, so in our case, I would say we're satisfied with accuracy, if that was your question. So already the graph networks, the previous work showed like incredible accuracy that is comparable to the ground truth simulators, and we have pushed it just a little bit more with the current work. And also, as I have shown in the experiment section, we can, if we move on to the bigger system, we can also tune the accuracy using the number of gradient descent steps that you use at the forward pass of the model. And in terms of time, yeah, we are still constrained to the fact that we are running on discrete time steps. So if you want to run on finer time step, you have to retrain the model. And like all other physical simulation models that I'm aware of, besides maybe NeuroDs, they work on discrete time steps. So I think it's, for now, we'll have to deal with that limitation. Yeah.
Okay, and then, yes, sure.
While you were checking for other questions. So I was wondering, your constraint function, that looks to me like an energy-based model, right? So, or at least, yeah. And then people there have used a couple of tricks to make those, so this inner loop optimization to work better. I mean, I'm wondering, so this Langevin dynamics and trying to make sure that my gradient descent is sort of finding the optimum in these 5 steps and so on. Have you seen any parallels or took over something from there, or?
Yeah, great question, because it's actually similar in the spirit to energy-based models, but I think we didn't have many of the issues that energy-based models have, because they care about actually learning the distribution, and we care about only one point, which is just the minimum of the constraint function. Also, another of our benefits is that we can initialize gradient descent to something that is very close to the minimum, so we don't have to like really traverse the entire space to sample, let's say, a good image in terms of if we're talking about diffusion models, let's say. So this, yeah. So what I've showed that the heat maps, we're just learning like the local neighborhood of the minimum, but if you go a little bit further, then the distribution might not be like what you would expect. So it's similar to energy-based models, but I think we tapped just a little bit into this area, and we learned like a very constrained case of energy-based models, so we don't run into those problems.
Okay, I'd like to conclude in the few minutes we have left with the same question that Olga was asking before to the first 2 speakers. So what are you most excited about the next developments in your research? Current or future work that you...
Some more seconds to think about it. Well, so I'm really looking for the unfolding this onto the real systems and see really where we can go with this. So I'm seeing at the moment in robotics this big trend with sim to real transfer. So everybody is doing stuff in simulation and then trying it for the real system and then essentially, let's say, hoping for the best. And I really love to see that we can do either this transfer more generically and be able to adapt on the real systems and make sure that we really end up with systems that are adaptive and not sort of just another way of creating kind of mechanistic or like stupid controllers.
Yeah, so in the simulation domain, I think, so for one, I mentioned that we have already achieved pretty good accuracy with graph nets, but if we are going to really beat the traditional simulators, it is still really hard, or it's really hard to convince people who use them to switch to graph nets, because graph nets don't have any guarantees. So one direction that might be exciting is how to actually provide some guarantees with the graph nets while still maintaining their accuracy and their scalability properties. And another direction is like what to do next with these models, with the simulations. So one exciting work that also came from our lab that Kim presented this early afternoon is that we can use pre-trained simulation models to get the new designs basically modify our physical environments so that the simulation goes as we want it to. Let's say direct the fluid to a particular location in the scene. So it is very exciting to see how these simulations can be used for other applications, maybe even for RL and robotics at some point. So,
so I see the start of a new collaboration maybe after this session. Okay, so we are at the end of this session, and in the remaining 30 seconds I'd like to ask you to please join me in giving a round of applause to our last two speakers. I'd like to thank them for two very exciting presentations and also for participating to this panel discussion. And finally, I'd like to thank you all for attending this session. I think in name also of my two colleagues, Olga and Dave, I hope you enjoyed it and you had good inspiration for your own research, if this is the case. And yes, enjoy the rest of the conference and see you around.